This is a MATLAB refresher for EGB242 signal analysis. The concepts here should be familiar from MZB126, but if they aren't, we'll start pretty simply so that everyone's on the same page by the time we finish. There's a sheet that goes along with this tutorial. It starts off with the introduction, saying that MATLAB, the program that I've got open at the moment, is a computational mathematics package which we'll be using to simulate signals, so hopefully we can predict their behavior in certain environments. There's plenty of resources on the MathWorks website. The website address is given on the sheet. Check out the videos that are available there. There's also all the documentation that you need for the program as well. To get your copy of MATLAB, you can either download it from the IT downloads page on QUT website, or go to OPodium for a USB. Let's get started. Question 1. Type help : to see what the colon operator does in MATLAB. So we can see that it brings up the description of what the colon operator does. In this particular case, it creates vectors at increments of 1. So we can use help for other functions as well. We type help space and what the function is. In this particular case, I've typed cos for cosine. That will be useful later. Using this information, create a row vector named x, which consists of consecutive integers between 10 and 20. So I'm going to create a new variable, x equals a vector that goes from 10 to 20, and I'm going to suppress the output using a semicolon. And you can see that since I pressed enter in the workspace, we've got a new variable that is a 1 by 11 double, so 1 row, 11 columns, double precision array or vector. I can double click on this to open it up in a new window and see that the variable x goes from 10 to 20 inclusive. I can close it there. In case you're curious, what I've done here to get my workspace in this area is I've clicked on this arrow, and normally that would say undock if it's already part of this window over here. So part B, create another row vector named y consisting of consecutive integers between 30 and 40. So new variable y equals 30 at increments of 1 to 40, suppress output. And we've got another variable that comes up in the workspace. Compute the element by element addition of vectors x and y. Store the result in vector z. New vector z equals x plus y. Suppress output. And we can see when we open vector z that we have 10 plus 30, 11 plus 31, 12 plus 32, etc. The only way this works is because x and y are the same dimension. Our addition operator is element-wise by default. Part D. Read the help file on the multiplication operator, star operator. So we go help star. And this means matrix multiply. Matrix multiply, keep in mind, is different from element-wise multiply, so just keep that in mind. That'll come up in a second. What is the difference between dot asterisk and asterisk? Let's try help again. Dot asterisk. Array multiply. So dot before something generally means element by element. So dot multiply is element by element. Dot that symbol is to the power of element-wise. The main thing to keep in mind when you have answers that you don't expect is to just check what your operators are. compute the element by element multiplication between vectors x and y. So we know that x is 10 to 20 and y is 30 and 40. So we can guess what our answer is going to be. So if we're doing element by element, we're going to have a 1 by 11 double. So the type isn't going to change and the size isn't going to change, but we're going to have 10 by 30, 11 by 31, 12 by 32, and 20 by 40. So we can double check that now. Element by element multiplication of x and y. I'm not going to put this into a variable, we're just going to look at it. And so we've got 300, so that's 10 by 30, so that makes sense. 800, 20 by 40. So it looks like that. So it looks like we've done that correctly. Use the MATLAB help or doc to find out the syntax to transpose a matrix. Useful resources can also be found on the MathWork website. And additionally, if you type into Google MATLAB space whatever you're trying to do, the link to the appropriate MathWorks page will probably come up. Or if it's something a little more specific, a different page with the answer that you're looking for will probably come up. So just because we're looking for transpose, this may not be right, but we'll just see, assuming that I spell it correctly. Help transpose. Okay, so transpose, and that's got a dot and then a, can't remember the name of that. So note non-conjugate. Since we're dealing with real numbers, we don't really need to worry about that. But just to follow that up, we notice dot, again, forgotten the name. So let's just check a couple of different options. So compute the matrix multiplication between x and the transpose of y. Let's look first at the transpose of y. So we can go transpose y, and you can see that our answer equals, has become a column vector. So that's one way to do it. Alternatively, since we've seen this symbol here, we can try y transpose, y dot, and these all give us the same answer. But you'll notice that the difference between the dot transpose and the regular transpose, if we had a row vector and then transposed it like that, that's all well and good. If we had an imaginary row vector, and then transposed it that way, we would get negatives, whereas now I'm going to press up to get my previous line. We had dot transpose, it stays positive. So that's where that non-conjugate thing comes in. So compute the matrix multiplication between x and the transpose of y. Matrix multiplication is without the dot, and then the transpose of y. For safety, we're doing it with the dot, different operator, obviously, and we've got 5,885. Remember that with matrix multiplication, there is addition as well. So if we multiply a 1 by 11 matrix or array by an 11 by 1, we'll end up getting a 1 by 1. Compare this with the matrix multiplication of the transpose of x with y. Store the result into matrix A. So transpose of x, matrix multiply y. So press output, and our result is an 11 by 11 double, because what we've done is we've turned x by transposing it from a 1 by 11 into an 11 by 1, and then matrix multiplied it with a 1 by 11. And so we take the outer two dimensions and we end up getting an 11 by 11. G. Familiarize yourself with the size command and use it to find the dimensions of matrix A. So back to our help, size, and we can see that size tells us how big each of the dimensions that our matrix has is. We've also got some other things that we can specify in order to get specific dimensions. So find the size of A, and we get 11 by 11, which is the same as over here. Okay, to finish off question 1, we're going to clear our workspace and our command window so we can start over for question 2. So we're going to clear our variable A, just so we can show that this can be done to one variable at a time. You see the workspace is no longer in there. Now I want to clear all of them. I'm going to type clear all, get rid of all of our variables. I can also type close all. That would close figures if I had them open. I don't at the moment, but you will find that useful later on. And also type CLC, which clears the command window. So on to question 2. Build the following row vector, x equals 2516. You can also put commas in between these values. You don't need to, but you can. Sometimes MATLAB scripts recommend that you do. So we've got our variable x in the workspace, 2516. Now we're going to add 16 to each element. So like before, we know that addition is an element-wise operation. So x plus 16, and that adds 16 to every element in x. And now part B, we're going to add 3 to just the odd index elements. Now, indexing is very important in MATLAB in that it saves you a whole bunch of time. If we're looking at an array x and I want to pick an element for the first element, I have regular brackets and then 1. If I want to pick the second one, 2 in the brackets. If I want to pick a bunch of them, elements 1 to 3, I have an array inside the bracket, which is the element numbers that I want. And now, for part B, what I want to do is pick just the odd index elements. So 1 at intervals of 2 to the end. And we've got our values of 2 and 1, so first and third. So now that we know how to access those, we can go those values equals x1 at intervals of 2 to the end. And when you use end, it doesn't matter whether there's an even or odd one, it just does it based on the interval. Plus 3. Actually, I'm not going to make that permanent. So those are just our options. If I wanted to, so we've got 2 and 1, adding 3 to both is 5 and 4. If I wanted to put those into a new one, I would have y1 at intervals of 2 to the end of the vector equals y1 at intervals of 2 to the end plus 3. And we can see that y is 5, 5, 4, 6. So I've just added 3 to each of those to the first and third elements. And now I'll clear y because I don't need it. So part C, compute the square root of each element. there is a function called square root, which is element-wise. So that's simple enough. Alternatively, you could try doing element-wise to the power of 1/2. So that's a bit of maths knowledge giving you different options to do the same thing. Compute the square of each element. Well, that makes things quite simple. Dot power of 2. So the sheet goes on to say there are many different ways of doing these exercises, as I've just demonstrated. MATLAB, again, being a high-level language, has inbuilt functions, which is really good to get used to so that you can use them. It'll save a lot of time. Let's clear the workspace again. Just as a habit, whenever I'm starting a script, I start it with comments regarding who wrote it and when and what it is, and then I start the actual code with clear all, close all, CLC. You can just write it on the same line, separated by a comma. Question 3. Familiarize yourself with the linspace command. It is important that you understand this command as it is used throughout this unit. So linspace is short for linearly spaced vector. So we've got a start point, x1, and an end point, x2, and this is the version that we're using more often, the number of points that we want. So n number of points linearly spaced between x1 and x2 inclusive. Build a row vector named t, which consists of 1000 points between the interval 0 to 1. Then compute the following. Something that is kind of important is that when we're looking at a t vector, we're usually dealing with periodic signals in this subject. So we don't want to go to 1 inclusive. So when we use linspace, we have to add an extra sample which ends the vector at 1 and then remove that 1. So that if we have something that starts at the beginning of every second, we'd start it at 0 and then 1 and then 2 and then 3. But if we have a vector that ends at 1, then we can't start it at 1 because our next sample will be 1 plus whatever the sample spacing is. So the way we get around that is t equals linspace start point 0, end point 1, and we want 1000 points, which you can write 1000 or 1e3. That just means 1 by 10 to the power of 3, and then just add a sample on the end. So we've got a 1 by 1001 double. Now we're just going to get rid of that last sample on the end. So t equals t element 1 to the last element minus 1. And watch the workspace, and it becomes a 1 by 1000 vector. So for part A, we're going to compute the following. Variable y1 equals natural logarithm, which in MATLAB is just log. If you want log base 10, that's log 10. I tend to, when I have functions such as this, I tend to write both brackets straight after each other and then fill in the space, because if you get to the end of a long line of code and you lose track of brackets, you may not have placed something in the right area. So natural logarithm of 2 plus t element-wise power squared. And from the order of operations, this power operation comes before the addition, so we don't need to put in additional brackets. y2 equals e, which is the exponential function, the power of t, and then you can see here that we've got two functions that are independently related to t. So we've got that e to the t multiplied by 1 plus cos 3t. So when we combine the two, it'll need to be a dot multiply. Okay, 1 plus cos 3 by t. And that works. y3 is cosine squared t plus sine squared t. Notice that the squared is after the function, so you would do the cos t first and then square it, and the same with the sine. So we've got cos t, and because we get a vector out of it, squared. We don't really need the brackets, but I'm putting them in just for emphasis. Sine t squared. y3, y4 equals arctan t. Arctan, I don't really use that much, but the MATLAB function for it is atan. These sort of things you just pick up either over time, or if you were to go to Google and type MATLAB arctan, it would pretty much immediately deliver you to atan. So a lot of these function names are based on what they do. So y5 equals cot t, and y6 equals sec squared plus cot t minus 1. So if you want to just make sure you don't make any mistakes, just use those extra pair of brackets, but you don't have to. Make sure you separate things so it's easier to read. And we've got our outputs there. We're going to quickly look at what these look like and just show you how to use the figure windows. So I'm going to create a new figure. You can just create a figure by saying figure and a new window will pop up, but I'm going to number this figure myself. I'm going to plot the t vector against y1, and that will come up shortly. When my computer has finished being difficult. There we go. Okay, we're going to plot some of the other signals with it as well. So if I was to plot t against y2, a new curve comes up. If we want to keep both of them on at the same time, actually, we can just clear the figure, CLF, clear figure, and then our window becomes empty again. We can plot t against y1, and then we type hold on to keep the previous plot on t y2. These automatically choose colors, but if we want to choose a color and a style ourselves, so t y3, and choose the color red, and I'm going to make it a dashed line, and this all comes under the help file of plot. And so we've got a red line, a red dashed line. And so we can add labels, X label, is time and the units, and that comes up here. You can do extra stuff to change the font, but that's probably unnecessary unless you really want to make it look pretty. We've got a Y label. In this particular case, it's amplitude, and we're not really looking at units. It's arbitrary units. Time, amplitude, title. Probably make your title a bit more descriptive than what I've put here. And we can also add a legend. And so we'll go Y1, Y2, Y3. Now legend should come up somewhere, probably around here. We can also change the location of it. You can find that in the help file for legend, or possibly still in plot. If we want to create a different figure, we can do figure 2, and we'll create a stem plot of t and y4. So this just looks at the discrete values. Quite a few there. So to make it a bit more visible, we can change the axis limits. So you have axis, and then a vector inside, which is the minimum and maximum x and y points. So we'll choose 0.1, 0.15, 0.05, and 0.25. So 0.1 is the minimum of the x-axis, 0.15 is a maximum, and 0.05 and 0.25 for the y-axis respectively. And you can see this is zoomed in, going from 0.1 to 0.15 and 0.05 to 0.25. And the stem plot just gives these discrete points. There are different ways to get a similar effect, but we'll probably be asked to use stem at some point. Let's assume that you add X label and Y label and the plot to it as well. Now I'm going to get rid of these plots by using our close all. There we go. And I'm going to move on to question 4. I'm going to get rid of my old variables. So question 4, a model to predict bacterial response to antibiotics as a function of time is given by equation 1. Plot this expression over the first 100 minutes. Choose a suitable time vector with an appropriate resolution. So first we'll create that time vector. We've got t equals linspace 0 to 100. Let's assume that the function is based uses t in minutes, otherwise it could be unnecessarily tricky. And we'll pick a resolution of 1000 samples again. Depending on your application, there might be like higher or lower resolution might be better. So press output, and then I can also, on the same line, write my next function, which is getting rid of the sample at the end. So if I'm going to do my function now, I'm going to do p equals 197273000 multiply. That just can be a regular multiply because it's only like a linear, it's a multiplication. And then we've got our brackets, suppress just for funsies, and then e to the power of negative 0.0313 by, new brackets, t minus 1913.25. And that has worked. So we'll plot it. I don't have to type figure if I don't want to. If I've got no figures open, that'll automatically open one. But the purpose of the figure, of naming the figures, is that you can choose them again once you've moved on to the next one. Okay, so since we've got our exponential function in there and it's negative, we're going to have an exponential decay, and starts quite high. Okay, and then we'll put in X label, Y label, title, legend, any zooming that's necessary to see the information, although the scale is already zoomed appropriately. What we're going to do now, predict how many bacteria will be left after 130 minutes. Let's try doing a actually, let's try finding, using that equation and just putting in 130. That seems simple enough. And then we'll look at it in a bit more detail. So we'll take away the semicolon so that it doesn't suppress the output. We'll take away an allocation to a variable, and we'll replace the t with 130. So that's our guess. But if we're going to create another t vector to see the path that it would take, new t vector, linspace again, 0 to 130, we'll need to maintain our resolution. So 130 as opposed to 100, 1.3 to the power of 10 plus 1, and then we can just take our previous and then we can plot T2 against P2 and see what we've got. So the answer is still very big, not quite as big as it was when it started. And that is the end of the sheet. I hope this has been useful. Remember to do take-home labs when you get the opportunity.